the path optimization for mobile sensor to monitor coverage holes in wireless sensor networks. I am Rebai. I am an assistant professor at the Vinci Higher Engineering School. And today I will present this research work which is realized by myself, Jinane, Charafeddine, Taha, Houda, and Wafaa, Shakir. So, as it is well known, today wireless sensor networks play a critical role in monitoring large physical environments. Personally, I have some contributions in this field, essentially related to wireless sensor deployment to achieve coverage and connectivity and tracking application. Currently, I'm working on path optimization for mobile sensor to monitor coverage holes in wireless sensor networks due to its importance in many applications like border surveillance or disaster recovering. To solve this problem, we have considered the sensing field as a grid, which is digitized into grid points. The distance separating each two contiguous points is equal to one measurement unit. So in this sensing area, we can deploy sensors, and each deployed sensors can cover all the grid points that have a distance less or equal to its sensing range, as it is presented in this figure. So, due to many problems that can occur, like sensor failures or energy depletion, or also suboptimal initial deployment, a certain region maybe remain uncovered. So a particular solution that can address this issue may be based on deploying a mobile sensor that can dynamically adjust its position in order to cover this blind zones in one tour. So our objective in this problem is to minimize the path of the mobile sensor such that covering all the blind zones in one tour, like this solution. We assume in this study that no obstacles in the sensing field. That means the sensor can move from each position to another, to each other any position without any problem. And we also assume that the mobile sensor can be configured to follow a predefined trajectory. Most approaches in the literature are based on decomposing this problem into two sub-problems. The first sub-problem try to determine critical positions that allow coverage holes, and in the second sub-problem, authors try to determine the shortest path or the shortest cycle of the mobile sensor using some algorithms like Discastra, Astart, or approximate methods based on PSO, particle swarm optimization algorithm, or genetic algorithms. Our approach here is different. Our approach focuses on optimizing the mobile sensor trajectory without restriction on the predefined positions. And this fact allows us to optimize or to dominate the literature solutions in terms of solution quality. So in our resolution methods, we first consider the grid as a graph. In this graph, each vertex corresponds to a grid position, and an edge, AB, may be occur if the mobile sensor visit first vertex A and then move to visit vertex B. In the second step, we try to determine the minimal number of grid positions to cover all the blind zones. Here, determining the minimal number of grid positions not mean that we will define the coordinates of these positions. We have just need to determine the minimal number without restriction on the coordinates of these positions. So after determining the minimal number of grid positions to cover all the blind zones, we will try now to minimize the total travel path of the mobile sensor. For the second step, which consists of minimizing the number of grid position to cover blind zones, we have proposed a binary integer linear programming model, which uses these decision variables xi that takes one if a sensor is assigned to vertex I and zero otherwise. Based on this decision variable, we can write our objective function like equation 1, which minimizes the total selected vertices from the set gamma, which represent the grid positions that are not covered, subject to the constraint number 2, which ensure the coverage of each uncovered position in the sensing area. Constraints number 3 are binary decision variable constraints. For the step 3, which consists of minimizing the total travel path of the mobile sensor, we have also proposed a binary integer linear programming model, which uses these decision variables. The first decision variable is called xi, which take one if the mobile sensor should stop at vertex I and zero otherwise. And the second decision variable is called yig, and it takes one if an edge is created from vertex I to vertex G, if the edge is selected in the final mobile sensor cycle, and zero otherwise. So based on these decision variables, we can write our objective function that minimizes the total weighted travel distance of the mobile sensor by selecting edges yig between visited vertices, subject to the following constraints. Constraint 5, that ensures that each uncovered point should be covered at least once in the mobile cycle tour. Constraints 6 and 7 ensures that each edge ig should select vertex I and vertex G. Constraint 8 ensures that each vertex should be connected to two other edges. Constraint 9 ensures that each selected vertex should have an outgoing edge. Constraints 10 are only directionally edge constraint. Constraints 12 and 13 ensures that each selected edge should have an outgoing edge. Constraints 14 and 15 ensures that each selected edge should have just one incoming edge, and constraint 16 ensures that the total number of selected vertex is minimal and is equal to the NB, which is determined by the binary integral linear model of step number 2. Constraint 70 ensure or constraint 17 or sub-elimination tour constraints, and constraint 18 ensures that the model remain giving a solution even if the solution is based on or is just one edge. Finally, the remaining constraints are binary decision variable constraints. So this method was tested on many grid size instances and many value of coverage range and density of sensors, of fixed sensors. And from this table, which summarizes the average computational time to solve an instance, we can conclude that when the coverage range increases, the computational time decreases. This result may be explained by the fact that when the coverage range increases, so the solution space expand and thus simplifies the search of a solution, despite the increasing number of the decision variables in the constraints. Our approach was also compared to the literature, to the recent literature proposed approach, which is the approach proposed by Kev et al. In 2023. And this approach is proposed to solve regular grids, as you can see here. So 7-7 grid, 10 by 10, and 13 by 13. So this figure that represents the percentage of dominance of our proposed approach. So from this figure, we can observe that our approach dominates the literature approach in terms of solution quality, and the gap increases when the grid size increases. Regarding the computational time, we can observe that when the grid size is small, the gap between the two methods is too small. However, when the grid size increases, so the literature approach computational time is better, and the gap between the two approaches increases. So, as conclusion, we have proposed an efficient path planning method for mobile sensor in wireless sensor networks to coverage blind zones in sensing areas. As a result, we have an approach that dominates the literature approach in terms of solution quality. However, in terms of computational time, the literature approach dominates our proposed approach. So in future works, we plan to try to improve the computational time of this proposed approach by adding, for example, some valid constraints that that may be developed based on the problem properties, and integrate real-time sensing and obstacle avoidance in the sensing fields. Thank you for